who will talk about full groups of Cantor dynamical systems and the interplay between group theory and Cantor dynamics.
Yeah, thank you very much for the invitation. So I'll be speaking English. I can get around like speaking Polish a little bit, but I'm not at the level to be able to give talks, math talks. So yes, my name is Constantine Medynets, and I'm at the United States Naval Academy, which is in Annapolis, Maryland, and so what I do topological dynamics, and I'm here visiting Artyom Dudko because we have a project. We actually published several papers together in the past, and we have a paper we are working on right now. I might mention some of the work we've done in the past. So, all right, and so we have some people online, as I can see, and all right. So what I'd like to discuss here is this concept of full groups, or more broadly, the idea of micro-supported groups, which is kind of a more recent phenomenon or idea where people actually started to notice that different classes of groups acting on trees, full groups, they all unified under this common idea of micro-supported groups. But my talk is going to be very dynamical in nature. We will watch just pure dynamics here. All right, let me start with going back to classics and discuss what we call Rockley lemma in ergodic theory. So what is that? So you have a measure preserving transformation. Of a standard measure space. And transformation T preserves the measure. And depending what you want to assume, if you assume some ergodicity, for example, of transformation, then there's a classic result that pick any set, then at almost every point, right, is going to return back to this set. So, and that's kind of there. And as you start to trace out the times when the points return back to the set, you get this idea of a partition of the space. So if you fix a set E, you assume that the set E has positive measure. And for each point, you can define a function that tells you when this point returns back to the set E. And for example, you could have points here. For example, this set, the point that returns to the set E after maybe 3 iterations. So, and the way we draw it, that's the image. That's the second image. And then those points will have to go back to the set E. We don't know exactly where they're going to land, but they're going to be somewhere in this set. Then you might have a different set here, and the points might return back, for example, after 5 iterations. Again, we don't know really where we're going to get back, but this is, we know that points will return. And in the end, what you're going to get what we call a Kaku-Tani-Rockman partition of the set. In general, you might have infinitely many towers. You're going to get smaller and smaller because we're talking about measure preserving transformations. And so the Rockley lemma is really what it allows us to do. It's really about the approximation of the original transformation by permutations within towers. So transformation T goes, every point goes up, and somewhere inside the set. But what if you keep the transformation S that takes your points up, and returns them back exactly where they started. So up, So essentially, you see that transformation S is equal to T everywhere except for the very, very top levels. And that's how the approximation is actually accomplished. Every transformation can be approximated by a periodic map. So there is this natural topology or metric that we can define as the set of points where the two transformations are different. And the topology generated by this set, by this metric, is called the uniform topology on the group of automorphisms. And this topology, set of periodic maps, is dense. The set of transformations is dense. So, there is a classic book of ergodic theory written by Halmos, and where he talks about this topology. He talks about there's a different topology on the group of automorphisms that comes from the unitary, the group of unitary transformations. And he discusses those two topologies here. So this other topology, which he calls the weak topology, because every transformation actually gives rise to a unitary map on this space. And as such, you can actually use topologies or topology, like any topology on the set of unitary operators you want, and actually bring the topology down to the space of automorphisms. So that's what he called the weak topology, because it's weaker than this uniform topology. The uniform topology has a ton of open sets. It's actually almost discrete. It's not discrete, but it has so many open sets for all, intended purposes. You can think of it as discrete. But this result, really, saying that since periodic maps are dense, actually really reveals the structure of transformations. Another interesting thing is that with respect to uniform topology, the ergodic maps, transformations are nowhere dense. However, actually, how do you see that? So ergodic transformations are nowhere dense in the uniform topology. And, well, the idea is that if you have a periodic map, and in this case, in fact, you can choose a small neighborhood around this periodic map that I drew, which would contain no ergodic transformations. And the idea is that if you have an ergodic transformation that is very, very close to this map, you can choose this set. You can choose this number so small that essentially the ergodic transformation will have to return points back to exactly where they started. So you will ruin ergodicity completely. So, okay. However, in the weak topology that I mentioned, come from the unitary group, ergodic transformations are they have this G delta. So what I need, but now we're going to switch to Cantor dynamics root, and this picture is what I really need. So there is actually a result. Here, everything here is measurable, all sets are measurable, there is no topology here. But it turns out that actually everything we talked about here works very, very well in Cantor dynamics. We have this homeomorphism of the Cantor set. And that's what I would like to switch to. But this is my animation that goes back to the 40s. Then it was used a lot in ergodic theory, this lemma, to establish, to work, get some results in orbit equivalence theory, when group actions have the same orbits, they don't have the same orbits, and so on. So, and now there's a parallel development in topological dynamics that probably goes back to the 70s or 80s. So historically, this motivation comes from, right, to study those things come from different sources. Applications to physics, and actual applications to operator algebras, again, which back in the day were all about applications to, at least presumably, to physics. So, because you have fundamental algebras, and using dynamical systems, and then using the cross-product construction was probably the most natural source of examples in fundamental algebras. And now that people started to look into, all right, we have this dynamical system, we have this operator algebra, how can you relate the properties of the two objects together? Similar development happened in topological dynamics, but instead of fundamental algebras, people work with sister algebras. So, and again, the same line of kind of resources, same kinds of questions, but again, the two theories, like at some point, become very different. But back in, the original motivation is kind of similar. It's here. This is the eraser, right? Yep. Now, so here, going forward, so X is going to be the Cantor set, and T is going to be homeomorphism of X. So the standard assumption here for me is that T is minimal. Which means that every T orbit is dense in X. In fact, so if you have a transformation, homeomorphism of a compact space, you can always find what we call, invariant subsets that are closed. But in this case, there'll be no, T is minimal because it has no invariant closed subset. So it's kind of a topological analog of ergodicity in some sense. I mean, not quite, but in some sense. Because the idea, right, if you go back, to the 1930s, it was that is there some condition that you can impose on the transformation that would ensure that ergodic theorem. Because the whole idea, right, was to have the ergodic theorem. And well, the first thing was transitivity, when there is one dense orbit, but that's not enough to ensure that ergodic theorem holds. It holds if that single orbit actually fills up the entire space. But that's not a mechanical motion, so people ruled it out. So minimality, again, is a different attempt, but in a sense, it still doesn't quite work out for ergodic theorem, but it leads to other applications. Now, so with minimality, what you can do, if you fix, we work with closed sets, closed and open, fix a closed set. And the fact that every orbit is dense, you can actually show that every forward orbit is dense. So in this case, and you can actually start with the map A, and same way you can define the function of the first return for your points. So you take the smallest integer such that the image of x is back in A. And this function actually is going to be continuous. So what happens is you have a continuous function on the Clopin set. It turns out that in this case, because A is compact, there will be just finitely many. So this function is going to be piecewise constant. There will be only finitely many pieces. And in this case, unlike in the magnetic theory, we have infinitely many towers potential. Here, we're going to get the similar construction. We'll get towers, but we're only going to have finitely many towers. And this finite partition actually will give us, it's going to become a partition of the entire space. So for every minimal transformation, if you pick Clopin set, you use a function of the first return to build towers above any Clopin set. And it will result in a finite partition of the set. So I'm going to write it down. So every Clopin set, a finitely many towers built upon A that form a partition of X. And so, now what do we do next? You start a Clopin set, you can usually take a smaller Clopin set inside. And essentially, well, the question is, what is the smallest height? The idea is to make those towers as tall as possible so that you can actually make the roof as small as possible to get a good approximation of the transformation. So same idea, it's like Fourier series. I mean, it's far, fetched kind of like an analog, but you use periodic transformations to capture properties of your dynamical system. So if T is minimal, every orbit is infinite, and in principle, you can take Clopin sets so small that lots of iterations of the set are disjoint. And as such, you can make the towers as tall as you want. You might have a hard time controlling how tall they are, but you might be able to control the smallest height of those towers. So that's the idea. And in fact, Cantor dynamics, probably since a paper by Neumann-Putnam-Skau and Skau from 1989, was all about kind of like studying those partitions of the space and how they are related to the dynamical system. How properties, control properties of partitions reflect properties of the transformation and so on. So it's a big part of the Cantor dynamics was really about that. And
So who were the authors?
so the results go back to like 1989. Ian Putnam, he had a paper. He had a paper where he essentially studied those categorical partitions. His main application was operator algebras, cross-product operator algebras associated with Cantor minimal systems. And then another different paper, I believe it was early 90s, it was three people, Herman, Putnam, and Skau, where they actually created a model. Essentially, there is a way to take all those partitions. And when you work with partitions, it's kind of a little hard because you have one partition, then you have a different partition. You can make them refine each other and so on. And in fact, there is a really nice graphical way to represent what's going on there. It's so-called the idea of Bradley diagrams. And that's what
Michel Armand.
Pardon me?
Michel Armand or something.
I don't remember the first name, to be honest
famous.
This I don't know. I don't know actually. It's like sometimes you have those papers, right? And you just know that all the names you memorize, but you really don't never met those people. So I've met Ian and Skau, and Ian Putnam and Christian Skau, but I've never met.
Giordano somewhere was the picture.
What?
Giordano was also there.
Yeah, but later. He came about just a bit later in the next paper. So essentially, they kind of open up this whole area. Ian Putnam, Christian Skau, and Thierry Giordano.
Richard Harmon.
Is it Richard?
Richard Harmon.
Okay. They started to really explore Cantor dynamical systems in the 90s, related operator algebras, related groups, and study the orbit structure. So, and how do you distinguish two systems? How do you know they have the same orbit structure or not? That's and it's a big part of like what they've been doing. And then they started to look into, okay, once we understand the z-axis, what about z-squared actions? What about actions quasi groups and so on? And that's where the field is going more or less. Actions of groups different from z, and can we understand the dynamics of that? So let me describe this model that they introduced, Bradley-Burchak model, which essentially what it does, and let me illustrate this idea here. If you take, this is my original clopin set A, if you take a smaller clopin set, maybe a piece here and a piece here, let's do this, there's just two towers. And now you can trace out what those points do. Well, they're gonna go up, up, up. Some of them maybe will go to this tower, some of them will go to this tower. And in fact, what you can do, you can start to partition your original tower into two towers or three towers, depending which tower your points are gonna go to. And then, so we have this tower, and if this tower is followed by this tower, essentially what you can stack them together. This classic cutting and stacking construction from ergodic theory that people have done, used it in so many different situations. But this is kind of just a topological version of it. So it's interesting. Burchak actually in St. Petersburg, he was working on what he called Markov compact or compactum, essentially, which is essentially the Bradley-Burchak diagram as we know it, but he didn't quite use continuity because continuity is important in topological dynamics, but he was staying in context of ergodic theory. So he used, for those ideas of cutting, stacking, trying to understand what's happening, how the partitions are related, isn't new. I don't know really if they knew about it or they came up with this idea independently, or it was already up in the air, ready to put together. But so in their result, they actually created a model that works for continuous homeomorphisms. While Burchak had those ideas and used them, but purely in the context of ergodic theory. He didn't care much about continuity. But that's very important when it comes to logical dynamics. So what is Bradley diagram? So it's a graph. It has one vertex at the very top, this 0. It has, and then I'm gonna just be drawing levels. Some people call it like a graded graph and so on. So you have vertices of level 1, you have vertices of level 2, you might have some vertices of level 3, and so on. And you connect the top vertex to the vertices of the level below, And essentially, you only connect consecutive levels. You're not allowed to connect vertices within the same level. Now, you're not allowed to leave like a vertex like that hanging. You have to connect it. There'll be no terminal vertices. Again, you're not allowed to skip the level. So that's an example of a Bradley diagram. Now, this first vertex here, that represents the trivial partition, when we just have one set X. The vertices and the edges of this first level represent the partition of level 1. So this one here will have 3 vertices, will be 3 towers. Each vertex represents a tower. And so this one has, there will be 2 paths. This one has a height 2, and this one has height 1. This next one has height 1 as well. If I go down here, I have 2 towers. That's my next level of refinement. And what is the height of this tower? Well, I just have to count how many finite paths I have to connect this vertex to the top. I have 2 and 1, 3 here. This one has 2. So I'll have my next partition is going to have 1, 2, 3, 1, 2. That's my next level of partition. But as you see, the vertices here are in fact, they connect the vertices from the level above. So this tower here, in fact, we're not talking about the order yet, but you can, if you imagine that, so what we do, we typically put some natural ordering on the edges as it terminates the vertex, so that you can distinguish which edge is first. So this is 0, it means that this tower is a subset of this tower. So the blue one here is going to appear in here somewhere. So it goes up 2 levels, and then we switch from this tower to the next tower. So now the dynamics will tell us that you go up to the top of the tower, and then you have to go back here. So that's how refinement works, how Bradley diagrams represent, finite partitions. That's the whole idea. And now, once soon as you have a graph like that, what do you do with graphs? Well, you can write out a bunch of matrices. You can look at the spectral properties if you want. You can do all sorts of things. And you can ask questions, does it tell me anything about dynamics? Because once you have the graph, you can count edges, vertices, you can do many different things. It turns out that, but here, this graph actually knows everything about the dynamical system, everything. So you should, in principle, you should be able to find how many measures, invariant measures does it have? What is the entropy? Is it, like a rotation on a group, or it's an expansive map? In principle, it might be hard, or maybe impossible because it's so hard, but you should be able to, because that's the model we have. All right. Yeah, so this model actually, and this is what made it so useful. Like for the past 20 or through 1991, it's like 30 years, really, people have been using this model, Bradley model, to actually study Cantor dynamics. And right now, we're trying to push it into like group actions other than Z. The problem is that there is no good model. So there is no good model for Z squared actions, for example. So yeah.
Some questions just to clarify. So from one dynamical system given x mu, so how many different Bradley diagrams you can obtain depending on the partition?
Well, how many partitions do you have? Countable many, right?
But how are they related to different diagrams?
Okay, so that's a good question. So yes, you have a the system homeomorphism have the sequence of partitions, you get a Bradley diagram. And then you get a different sequence of partitions to get a different diagram. They will look absolutely different. So, however, it turns out that because they came from the same system, there's this nice procedure when it comes to Bradley diagrams is that you can erase levels. You can, for example, remove this level, and what you do is just concatenate the paths. This is called telescoping. So if you have two Bradley diagrams and they came from the same system, there'll be yet a third diagram such that if you telescope it to odd levels, remove every even level, you'll get one diagram. But if you telescope it to the other level, to the to even levels, you'll get the second diagram. So they are isomorphic.
So not necessarily there is a telescoping of one and telescoping of two that they all coincide, but they will become kind of connected through the third diagram, yeah?
So it's yeah. And yeah, I know that Lena Carpel is watching online, she might clarify that. So
Yes, I think you are correct. There is a third diagram saying that telescoping with respect to odd levels gives telescoping of the first, and telescoping with respect to even gives telescoping of the second.
So what I'm thinking about, because there is this notion of strong orbit equivalence, and what we discuss is really about strong orbit equivalence of the systems. But when it comes to isomorphism, that's definitely true, but there may be more. So I just can't quite recall all the time.
Yeah, that was for strong orbit equivalence.
So this is definitely true, because to your question, but there might be more rigidity there. There may be even more that you can get. Honestly, I've never looked into this question. So, okay, let me give you some examples here. The first one is, let's take a two odometer. So what is the odometer here? You take the space of, say, two adic integers, 0, 1 sequences. And the transformation, what it does, it just adds 1 to every group element. So it's rotation. And so, for example, if you have a sequence like this, something, and you add 1, but I add 1 on the left. So 1 plus 1 is equal to 2, modulo 2 is equal to 0. And then you have to carry on to 1 to the next place. So that's the image. And what happens if you add 1 again? Well, we get 1, 1, 1, 0, 0. What happens if you add 1 to this element? You'll get 0, 0, 0, 1, 0. That's how it works. And there is a tail there, which doesn't affect the tail. Now, Bradley model for that, it looks like this. That's 0, 1, that's 0, 1, that's 0, 1, that's 0, 1. So you have a diagram with the edges, with partial ordering on the edges. And the path space is the set of all infinite paths that start at the top and go all the way down. You're not allowed to kind of go down and up, you just have to go straight down. That's a path space where the topology is that the accused paths are closed if they share large segment, and that becomes a Cantor set. So, and the ordering now allows us to define homeomorphism. So you have what we call the Virchow map. You take any path and you want to, this is the path, and you want to know what the image is. And you pretty much use the same construction, the lexicographic. So you have to start from the top, trace all the edges, and find the first edge that is not the largest. When you have two numbers, 0, 1, not the largest means that you are 0. So, and it's essential, the image is, you don't change anything below, but 0 becomes 1, and then all the 1s become 0s. So that's the same model. More generally, if you have a dynamical system, a Brandl diagram, it moves. Sounds like that. You always have some kind of ordering on the edges, and you only order the edges that have the same range. 0, 1, 2, 2, 1, 0, 0, 1, 2, 1, 0, and so on. And this ordering allows you to define a transformation on path space of this system. The problem is that it doesn't always lead to a continuous map. Sometimes you cannot extend it to a homeomorphism of the entire space. Because what happens is there'll be always exceptional paths, which we call maximal, minimal. For example, you can take 1, 1, and so that's a maximum. Or it can take something like 1 and 2. So essentially, as long as you follow the maximum edges, you'll get a maximum pass. Or minimal pass if you follow all zeros. It's always non-empty. And what happens here, like all 1s go to all zeros, maximum paths have to be mapped to minimum path. And the way it works, it might not always work continuously. So it's not always homeomorphism. So for Burschik back in the 80s, it was not a problem because he didn't care about continuity. You could throw a setup like measure 0. Throw out a setup measure 0. Here, it's a big, big question. And so in fact, some diagrams doesn't have continuous dynamics whatsoever. That's so I believe I was in Turin at the time. I came up with this example. So this diagram actually does have a continuous dynamics. There's no way to assign an ordering that would lead to a continuous dynamics. And by the way, Brandl diagrams, is a good way, allows you to see the structure of the system. Like if you take this sub-diagram on the far left, that's a minimal component actually, because if you have a path inside of it, it will stay inside of it. There is no way for that path to switch to a different vertex. If you have a path here on the right, it will stay inside of it because it's not going to have, there's no way for this path to switch to a different vertex. But if you take a path in the middle, because now you see where edges connecting the vertices here to the vertices on the left, this path can go left and right, depending on the order, but its orbit would come as, as close as you want to pass on the left and pass on the right. So the pass here will have a dense orbit. The pass inside it will be minimal component. This will be a minimal component. So this diagram has two minimal components and some points in between that will make the system transitive. However, there is no z action on the space that defines, that follows the structures diagram. So Lena Karpel certainly this over the young Kwiatkowski, they did a lot of work studying when diagrams have continuous dynamics. So trying to relate the internal structure diagram to because this question of when can you extend a continuous map to a homeomorphism is probably as old as, I don't know, it goes back to 1930s. But here the question is, can you extend a map to a homeomorphism of the Cantor set by still preserving this combinatorial structure? So that's kind of like the question. Okay. Mentioned, essentially for the past, I'll say 20 years or so, people have been looking into different classes of systems, substitution systems. topless systems. And they were trying to understand what a Brattle-Virch model would look like for those systems. Is there some particular structure that you can see in the Brattle diagram? So, and so let me know, raise your hand if you've worked with substitution systems before. So just let me remind you what it is. So we're working with subshields. We have an alphabet. Find an alphabet, and you look at the subshield. So that's a full shift over that alphabet. It's not a substitution system, but now inside of the subshift you have lots of different subshifts with different properties. A particular example comes from what we call the substitution rules. So you pick, for example, or let me give you an example. You have an alphabet with just 2 letters. And now, let's take a following map that A goes to AB and B goes to A. And let's iterate this map. So this is sigma. Let's see what happens. A. So if you substitute AB for A, you're going to get AB. Then you substitute again. So A, the first letter goes to AB. B goes to A. That's the second iteration of this rule. Let's do it again. A goes to AB. B goes to A. The first two and the last one, A goes to AB. You can take a substitution rule and iterate it, and you're going to get longer and longer sequences. And in fact, oftentimes there will be a sequence that is just stationary. This one actually, as you see, we start with A, then AB, then ABA. Each next iteration extends the first one, the one before. And it will converge to a long sequence, and it takes a subshift generated by that sequence. So, and that's what we get called a substitution system. The beauty of it is that it's there's a lot of combinatorics there. Those rules capture actually, dynamics quite a bit. So, and those are beautiful class of systems. They use as models for not quite one-dimensional model for quasi-crystals, so some people study them, and so on. In this case, so people looked into Brattle diagrams for substitution systems. Fabian Giordano published a paper, I believe in 1999, where he described Brattle diagrams for substitution systems. It turns out that they all have what we call stationary diagrams. Something like, for example, this one. There is some technical parts to that, but roughly speaking, what you do, you have 2 layers A and B, and you should be able to see the same picture over and over again, and the same order over and over again. For example, 0, 1, 2, 0, 1, 0, 1, 2, 0, 1, 0, 1, 2, 0, 1. If you have a diagram like that, what kind of substitution does it correspond to? Well, you look at this is A and this is B. You look at A, and you look at A is connected to A. So you go to A, then goes to 1 goes to A, so you connect it to A, and then to B. That's the first rule. The next vertex will be what? A and B. Simply in this order. Station diagrams will give you a substitution system, and in fact, Fabian Duran proved that they are homeomorphic or isomorphic as a system. And there is a reverse procedure. If you start with a substitution system, you might have to tweak it a little bit, but you can always construct a stationary Bradley diagram for those systems. That's kind of like one line of work. I have a paper with Jan Kwiatkowski, Sergei Bezuglia, and Boris Solomyak where we, generalized his result to non-zero minimal systems that substitution systems that have some non-trivial minimal components. And so people looked at toplet systems. I'm not going to state the result, but it's classified what diagrams you can get. There is a beautiful paper by Domnarovich and Alejandro Manas, our own Domnarovich from Wrocław, and he proved that if you have a diagram that has the same number of vertices at each level, so it doesn't change. What kind of system is that? Well, there are two options, as it turns out. Either it's rotation, it's an odometer, like the one I have there, or it is an assumption. So there is a nice dichotomy there, actually. Sometimes systems can be neither, as we know. They don't have to be equally continuous, they don't have to be rotations, or subshapes. They can have both pieces there. But for diagrams with the same number of vertices, there is a dichotomy, actually, which is beautiful. So a lot of work has been done kind of trying to describe Bradley diagrams for particular classes of systems and so on. Another thing you can use diagrams for is to describe invariant measures. So of the system. There's actually nice, interesting combinatorics there that you can use. So since we have a homeomorphism, it has at least one invariant measure. It might have more than one invariant measures. And you can actually just, if you have a Bradley version model of homeomorphism, you can look at the diagram and understand how many measures does it have. Well, this one has one, because it's stationary. Sometimes, now if you have the same number of vertices, for example 10, you can have at most 10 erratic measures. That's actually kind of a fact that we established. And now if the diagram, number of vertices grows, well, that's difficult. that is difficult. I know that Lena Carpet is studying invariant measures for various diagrams with different number of vertices and so on. But let me give you this kind of like where this comes from. So if you look at the matrix, this diagram, you can describe what we call the incidence matrix of this bipartite graph, just between the two levels. F1 here is, we count how many paths we have from this vertex to this one. 2, how many goes across? Just 1. And same with B in the second row, 1 and 1. So just given the Bradley diagram, you get different matrices. The matrices don't have to be square, if the number of vertices change, they're going to be just kind of rectangular matrices. But that Bradley diagram gives you a measurable partition of your Cantor set. Now, let's take a look at this open set on the left and this open set. If the measure is invariant, the two sets would have to have the same measure. Now, and in fact, if you fix one of those sets, you see that it naturally breaks into, there is one extension here, a different extension, and the third extension. So you can actually partition the open set from your diagram into open sets that come from the next level. So if this is level 2, I denote the value of the measure of this open set by P2. P2, that's a vector. So P2 is the value of the measure mu on the base of the color to the vertex V. So towers, essentially the vector Pn, you just assign, you have a bunch of towers, you simply take the measure volume, the measure of this side, the volume, the measure of this side, and so on. That's your vector. And you can check that those vectors satisfy the following algebraic identity. So if you have this matrix on the diagram, and you take its transpose, you can actually reconstruct the measure at the level above if you knew the values of the measure at the level below. So this is kind of a recurrence relation. Now, and in fact, if you just study those recurrence relations, you'll be able to describe all measures. What happens if you have the same matrix? It's stationary. Well, in this case, you simply have this. Or you can raise it to the nth power and go to, m levels down. So you get, and now you study iterations of the one matrix and how the term probability theory that answers those questions. It has, for matrices, right, it's all about positive, there's only one Frobenius vector, an eigenvalue, and that will give you the unique ergodic measure. Yeah.
So each sequence of these vectors Pn satisfying this recurrence condition defines an invariant measure.
That's right. That's right. And now, what if you have like 10 vertices at each level, but the matrices are different? Well, the matrices here are all kind of the square matrices, but they're different. There is this beautiful theory from the 60s, like, I think it's called Birkhoff, not the same Birkhoff like as ergodic theory, but someone else who studied those products of matrices. And those matrices, what they do, if you have a cone of positive vectors, matrices have positive values, entries, they preserve the cone. And you can think about this relation is that what happens to the cone of positive vectors as you bring it up? Well, they start to collapse, but you cannot really take the cone that has extreme edges like that and turn it into round cone. There is no way. It's going to still be simplicial, meaning that it has those dedicated edges. Going to look like this. And in the end, as you take the limit of these cones, you'll get something like this. You might get a single ray, you might get, which would correspond to the unique measure, you might get a sector like that will give you 2 ergodic measures. You might have like a cone like that will give you 3 ergodic measures, but there is no way for you to get a round cone. So that's how for systems with diagrams with 10 vertices and so on, or a finite number of vertices, which is the same, at most you can get is the number of vertices of ergodic measures. And that comes from that, generalization of the Giordano-Putnam-Skau theory. Yes.
So you start from, say, 0 level and go down by taking 3 images of cones after F transposed? Or
well, no. This one, this is at the level n plus m. You take the cone at that level and bring it up. And when you do that, you multiply multiply the matrices. And the cone might, if the matrix is, say, non-invertible, right, it might collapse certain faces. So it collapses faces, but it does not add the extreme rays.
But you have only finitely many levels to go up. How do you take limits?
Yes, that's right. But now the diagram goes down. To reconstruct the measure, you have to bring it all the way. So you just take the limit. Okay. When n goes to infinity. Yeah. Anyway, that's kind of a thing that I find really fascinating. That's so beautiful because you can now use some results from matrix products and other things. It's a beautiful combinatorics. Just one example. This system run across. This one has one guide measure, unique guide. And in fact, what's behind it is that if you take the series 1 over n, it's divergent. So, what if you take the diagram whose matrix looks like this? 1 over n squared is converged as far as I know. And it turns out that this diagram actually looks like it has a similar structure. Hold on. 2, it should be 4 here. It should be 9 here. and so on. Well, this diagram actually has 2 guide measures. So you can use some interesting kind of like asymptotic results to build systems with different number of guide measures. Yes?
Wait, so is it like a full theorem? If you take any series that's converging, that you get more than one encoding measure, and if you get the divergent system?
So it's, I mean, for diagrams that, so let me put it this way. Lena Carper, who's online, might be, in a better position to answer this question because she studied a lot of them. But for diagrams are messy.
Yeah, so here you can take some function f of n instead of n or n squared, and if the series 1 over f of n is convergent, then you have 2 measures. If divergent, you have 1 measure.
But in some cases, yes, you can give a full theorem, and at least for diagrams that can be clearly defined. Yeah.
Also have one more question. Okay. So you said that there's a theorem that if you have a fixed number of vertices at a level, then you have at most this number of encoding measures. What if you have like perhaps different number of vertices but bounded? So at every level you have at most 4 vertices.
Yeah, because
it's
you can tell the scope, the diagram, you can erase vertices, you can always reduce it to this case when you have the same number of vertices.
Okay, so it still works.
Yeah. Yeah, you just take a subsequence of vertices. Okay. All right, so diagrams, tell you like a lot about dynamics. You can vary measures, you can decide if it's a rotation or, at least in some cases, or an expansive map, and so on. You can study, there are some algebraic invariants, you can assess so-called dimension groups, if you know what they are, you can assign there from that. You can take different inductive limits of groups here to actually get a lot of information about the group. Now, what I'd like to switch to is talk about this idea of micro-supported groups, or in my context, I'll be talking about full groups. So, you have a dynamical system, xt. X is a Cantor set, T is a homeomorphism. And we can define, let's call this object, f of t. So what is that I'm taking? That's going to be I would like to redo it slightly. So I have X in the Cantor set, and G is a group that acts in the Cantor set. So the full group of G, or to be precise, of the action of G, is the smallest group that contains the group G, because we want to expand the dynamics. That's what is a group. We need to take the kind of the largest group in some particular sense. So we take the group G and we add more elements to that. The smallest group that contains G, and if you have a countable partition. And G1, Gn some group elements. And the mapping H from X to X that is defined like this. At each element AI, we simply take Gi. So, and what I would like to do, and if this mapping H, it doesn't have to be a homeomorphism because it can actually mess up images. But if it happens to be a homeomorphism, then the full group will contain H. So it's a kind of a long definition. I will explain it. So we take our canvas as X, we take a partition, and then in each, you pick a group out some group elements, G1, G2, G3, and you just piece them together, you create a new homomorphism that on this set acts as G1, on this set acts as G2, and so on. That gives you a countable group, which we call the full group. So it's a piecewise, regluing process. Whatever, those constructions appear in many different areas of mathematics. So, but here what we do, we extend the group action to this construction. This is called the full group of the dynamical system. Now, an analog of that actually, it doesn't come from a group action. Thompson's group would be this famous which appears in groups acting on binary trees and so on. So what is that? So you take a binary tree, 0, 1, 0, 1, 0, 1, and so on. And those are all, they're not automorphisms of the tree, but they act as the boundary of the tree. And essentially what you do, you take two partitions of this set. So fix two partitions. Of the boundary, meaning that you fix one element here, and another element here, another element there. So all the sequences that start with this so you fix two partitions of the boundary, and the two partitions have the same number of elements in it. And the homomorphisms that you define, gamma, what they will do, if you take xi and something else, the tail, what you do is just change the prefix, but you don't change the tail. That's how Thompson group E is defined. You just rewrite the prefix of gamma. So it's similar in spirit, actually. You take partitions, and whatever, if you can connect atoms from one partition to another one, you define group. A group. So theorem. The full group is a complete invariant of continuous orbit equivalence. What does it mean? So you have a dynamical system at x and g. That's here. Right above it, you have a countable group. There is no action anymore. You forget about the action. That's simply a group. You take a different dynamical system, and you take the full group for that dynamical system. Continuous orbit equivalence. What is that? So it means that orbits are the same. You can have a homeomorphism from here to there that just send orbits to orbits. But more additionally, so locally, that's not enough, that's simple orbit equivalence, but continuous orbit equivalence means that there is an extra constraint there that actions are locally kind of the same, roughly speaking. So, now, you have this countable group here, countable group there. It turns out that if you have an isomorphism between two groups, you can actually, this isomorphism always comes from a homeomorphism of the two spaces, of the two systems. So the diagram actually commutes in every direction. Like this. So you can reconstruct the system from this object. And it goes back to, historically, to like 1960s, Henry Dye proved something like that in ergodic theory for measure preserving transformations. And then Giordano-Putnam-Skau had this result in 1999, but for z actions, for minimal z actions. And they tried to follow Henry Dye's ideas. In 2011, I had this result optimized for general systems. In other words, this group remembers everything about the system up to continuous orbit equivalence. For example, entropy. The new result here, recently, that entropy, topological entropy, is preserved by continuous orbit equivalence. It's actually pretty big. And the question is, can you find this number, the entropy, inside this group? For example, what about ergodic measures? If you have a system that is uniquely ergodic and a system that has two measures, it cannot be continuous orbit equivalence. What is responsible for the number of ergodic measures inside this group? Is it algebraic invariant that captures that? So the field actually is moving towards this idea, relate dynamics here to algebra up above. What Artyom and I have been working on, we study characters as group characters for groups like that. And it turns out that characters actually responsible, they count the number of ergodic measures. So that's what we did, and we continue to work on that.
But for now, only for G.
Yeah, I mean, there are some technical constraints, yes, but overall, philosophically, what we're doing right now is, right now we've done it for G equals Z, for the integers, but it's still far from trivial, actually. But this group remembers, characters are responsible for ergodic measures. What is responsible for entropy? We don't know. Can you tell if this system is, for example, minimal or not? If you look at the group. So what is the most natural notion of minimality for the group? If an abstract group, minimal systems have no closed invariant subsets. Proper. Normality, right? Is a group simple or not? Does it have normal subgroups? Normal subgroups should be somewhat responsible for invariant subsets. It turns out that yes, the group is, there are some technical details here, the commutator subgroup to be precise. But the group is simple if it links the dynamical system below is minimum. Or to be precise, the commutator subgroup is simple if the group below is minimum. That's kind of interesting result that's recent. What else? You can actually decide if the system is a subshift. It turns out that actually Matsui did that for Z actions, and he found that for Z actions, the commutator subgroup of this group is finitely generated if the linear system is expansive. So there are things that you can capture. Nekrashevych has pushed those ideas to include groupoids and some really, really fancy objects. Okay. Another thing that is this, for Z actions, for example, minimal Z actions, this group is a minimum. It was actually a big result that if you put all the properties together, you have you're going to get the group that is a minimal, simple, and finitely generated. And those were the first results, actually, of the first examples of groups of that sort. Prior to that, there were no known results. Right? There were no known groups that could satisfy all three properties. And so what's interesting was Grigorchuk, we just overlapped with this conference in Chile in 2010, because I was studying orbital theory, full groups, but from the point of view of just orbit equivalence theory. Do they preserve orbits or not? Can you recover orbits? And we talked with Grigorchuk, and he told me about, somehow he had this really good intuition about this group, because at the time, no one in group theory knew about this group, really. It was primarily people in dynamical systems, and maybe some operator algebras. And there were very few results about algebraic properties of this group, except for Matsui result. So Grigorchuk somehow realized that there is something there, and we conjectured that, well, this group would be a minimum. So, and after this peak, kind of like starting from 2012, after speaking, the past 10 years, there have been a lot of different results about those groups. What properties does it have, what groups you can embed in them, and so on and so forth. And recently, it turns out that what's really important about those groups is, yeah, it's important that they come from dynamics, from group actions, but what's really important is that they are micro-supported. What does it mean that the group is micro-supported? If you have a group acting on some space, it is micro-supported. If for n equal to set A, there is a group element G that is trivial on the outside of A and but acts non-trivially inside A. So in many results, what's really behind the proof, once you understand what's happening, is this idea that the group has lots of elements with small support, and they're everywhere. And then that's what kind of like, and now that allows us you to connect this theory to maybe groups acting in trees, because many of them are micro-supported as well. Thompson's group, again, that's a group. It doesn't act on tree per se, but the tree acts on the boundary of the tree. But this group is also micro-supported. And by the way, this group has no characters, so it has no invariant measures. And it was hard to prove that this group has no characters. So again, this idea, this connection that characters and measures, they go hand in hand. So I think I'm gonna stop here because it's like 10 minutes earlier, but I feel like it's a good place to stop, and I'm happy to answer any of the questions. Thank you. So questions, what are the open questions here, for example? Amenability. Is this group amenable for Z2 actions? The answer is no. There are counterexamples.
It's a short open question.
But we need to understand what systems it is a minimum. So, what systems it is a minimum? We don't quite know.
Do you have any intuitions?
So we know that it's a minimum for rotations, for odometers. That's what we proved, but it should be some sort of definitely for like probably template systems, extensions for rotations and so on.
Okay, so when is it not amenable?
If it has some kind of it's a good idea. It has some kind of special direction that looks like a full shift. That would be non-amenable. Full shifts have non-amenable full groups. So and multidimensional groups they have a direction, but there is no conjecture. There is no good conjecture for that. Relations, defining relations.
Mm-hmm.
That's actually the question here is there a group that is simple, amenable, and finitely presented? That's still an open question. And the conjecture is that you have to go to some kind of a multidimensional subshift of finite type and mess with them and just possibly get something like that. So, in general, can you describe relations? With Grigorchik, we were able to describe relations like that that's in the sense that it's possible. But now, can you maybe, if you use additional information, substitution system, can you say more about relations and so on? And entropy, can you find entropy inside the full group? So, okay, we have people online.
May I ask a question?
Yes. We met a long time ago, and probably here at some conference.
Yes, I remember. So I really enjoyed the talk. Thank you. And I was intrigued by your comment when you were still in the first part talking about the Bratelli diagrams. And you said that there's a problem if we want to consider more than a homeomorphism, right? So let's say we are considering a Z2 action. Because there is a similar situation for flows, R actions, and multidimensional flows. So for flows, we have this Kakutani-Ambrose representation theorem, which is the same idea, but of course, you have this roof function, right? The suspension. And there is a construction which is not so trivial, actually, maybe very non-trivial by Katok for multidimensional flows using cocycle theory. And so your comment intrigued me because it seems very related. And I mean, I can imagine that there exists a theory also. I mean, obviously you can try to generalize the side of the Bratelli diagram and try to invent like a diagram which has let's say several directions. It's obvious, let's say down and to the. But what's nice, of course, with the Katok theorem is that it's a characterization. It works in both directions. So if you could comment on this.
So, okay. I know the result that you're talking about. I looked into that a while back. I couldn't quite understand how to make it work in the context of Cantor dynamics at the time, but maybe, it would be a good idea to revisit it. So what people try to use some people call it Voronoi partitions or tessellations, really, because you can start with tilings of the group that acts. The problem is that, but maybe it's inevitable, maybe there is nothing you can do about it, is when you have a partition, you're going to get your partition of the space. Right now they have this nice little structure that look like towers. But more generally, you're going to have some kind of a sets like that, and the group, for example, for Z2 actions, you can act in every direction, and then you have another tower of your partition. The problem with that, the boundary becomes a problem because we can't really control the boundary. For Z actions, the boundary is just a point here and point there. It's easy to control, it's easy to understand. For Z2 actions, the boundary might be very, very complicated, and again, maybe that's the way to do it, but it has been very, very difficult to work with that. But again, for Cantor result, I've read about it a long time ago. I somehow couldn't quite figure out how to apply it. But you know, if you have if there is a way to rewrite it for just Cantor system, that would be amazing.
Okay. Okay, thank you.
Any other questions, comments? Okay. Is there no other questions?
All right, thank you.
Yeah, thank you very much. Very, very nice talk. Thank you.